It is the 10th seminar in this series of Wednesday nights on Petri nets, and it was a very interesting experience. So we hope that it helped people to feel not lonely, people who are doing research in Petri nets, and at least for us, it was really so great and so just motivating. Today, so now it is end of April, and actually the summer is coming, and we think that for now we make a break, a pause, so till the next academic year, when we hope to continue this nice experience. We hope that it will be so helpful and interesting, not only in when it is pandemic and when we are all sitting at home. And so, of course, we also hope that in a year, so just not in a year, in half a year, we'll have much better circumstances and still, so just such seminars online when people from different countries and continents can meet. So it's really motivating and interesting and gives us enthusiasm. And today's speaker is so just our guest speaker from Melbourne, and that's why we start in the morning. Anna Kalenkova, she is a research fellow in University of Melbourne, and she did her PhD in Eindhoven, and she has some prizes in process mining, and so these are so just best paper award in process mining conference, and also best paper, best journal paper in SOCIM journal. So it's really, we are very happy to greet her here. And the topic of today's talk will be about repair, so just repair process models, and it will be a kind of continuation for our previous talk made by Alexei, but it will be another view on the problem, which is also very interesting to look at and to compare. So I'm happy to announce Anna's talk. Anna, you're welcome.
Hello, everyone. Irina Alexandrovna, thank you very much for your warm welcome, and I'm happy and honored to present my talk here. Yes, it's actually the continuation of the previous work that is driven by Alexei, and that is about process repair, although it's this work goes into a little bit different direction. And I would be happy to discuss differences of our approaches. So this work is titled Automated Repair of Process Models Using Non-Local Constraints. And this is our joint work together with Joseph Carmona, Artem Pliviani, and Marcello La Rosa. So let's start. I'm sorry. So we all know process mining. For those who are new to process mining, I can list the main algorithms. So these are process discovery algorithms that take event logs of information systems. Usually these are process information systems that run some different processes in different domain areas, and they generate event logs. So discovery algorithms.
Sorry, Anna, do you aware we do not see your slides?
Oh, I'm sorry, I didn't know that. Let me share it again. Sorry, can you see it now?
Yeah, we can.
Yes.
Oh, I'm very sorry. Okay. And what about now?
Yeah, fine.
Great. Sorry for that. Yeah, so here we have a general schema of process mining algorithms. Yeah, I think many of you know it, but anyway, we have to list them. So we have process information systems that represented here as GRs, and they generate event logs that further analyzed by the process mining algorithms. And the first type of process mining algorithms are discovery, that take these event logs and they try to generalize the behavior recorded by information systems, and they try to construct process models. So here you can see an example of process model that here it is a Petri net that contains different activities, different transitions, A, B, C, D, E, F, and E here. And it was generated from event log. And usually process models more compact than these huge event logs. And since we have this model, we can analyze it further. And also we can find the difference between a process model and an event log. And this type of algorithm is called conformance checking. We have an event log and we have a process model. This can be a process model that was automatically generated from a given event log, or this can be a reference process model that represents the behavior we want to see, and we want to compare the log against the model, and we want to find the deviations. We want to find the common parts, and we want to find where we have discrepancies. So this is how conformance checking algorithm work. And the last part, the third type of algorithms are enhancement algorithms that take a process model and an event log and extend a given process model with additional information from the event log. So talking about repair algorithms, we will discuss discovery algorithms and enhancement algorithms, because repair algorithms help to improve the process model that was already constructed from an event log by adding additional constructs or changing it so it aligns with the reality, so it fits the real behavior that is represented by the event log. So let us consider a simple example. Here we can discuss a simple structure of an event log, and for our algorithm we only need 3 columns here. That is a case ID that represents the execution particular instance of the process model being executed. The activity name, that is the name of the event that happens in our system, and the timestamp. In our algorithm, we do not need particular timestamps. We need timestamps only to reorder the events in accordance with the time of the execution. So we take this table and we transform it to a set of traces. So we consider an event log as a set of traces where each trace is a sequence of event, and each trace corresponds to a particular execution of the process. So we first filter this table based on the case ID. So we take all the rows from the table with case ID 1, and then we order activity names according to their timestamps. So here how we get the first trace, and similarly for case ID 2 we get the second trace. And what is this process is a motivating example, but it was taken from a real live BPI challenge event log. So I consider this event log as a motivation. And here we have only 2 traces. So this can be considered as a banking process. So first, the user sends an application. So this can be a loan application. This then on the bank side, the application is checked. If all good, the client is notified and then it is accepted. However, the application can be created on the banking side. So the bank employee creates this application, then again, this application is checked. And then there is no need to notify the client. The application is completed and the application is accepted. So there are 2 cases. And how, so we can represent these cases as a directly follow graphs, and this is what actually usually all well-known process mining algorithms such as inductive miner and split miner do. So first, they construct a directly follow graph from an event log. So we have a graph where each node corresponds to a particular activity or a particular name of the event, and we draw an arc if there is if there is such a trace that one of these events goes after another, we draw an arc, and we construct such an intermediate model. And this how now the most popular process mining discovery algorithms work. They first construct the directly follow graph, and then they cut this directly follow graph, and they construct a different, more sophisticated model. But this is an intermediate representation. And also the commercial tools such as Disca, such as Celonis, they also construct this directly follow graphs, but as a final representation of the process. So now let us take this directly follow graph and apply split miner and inductive miner. In these cases, we get the following process model. So here we can see a Petri net that is a free choice Petri net. So when we already deal with direct follow graphs, we can only construct free choice nets out of these graphs. So what does it mean? So free choice means that at any particular state of our model, we are free in our choice. We are free to decide which activity to execute next. So here, after check application, we can either execute notify client or complete application. So at this step, we have already lost the previous history, the previous history of the system execution. When we do check application, we already do not remember what was before. And this is why we get this Petri net model that is free choice. So if we have a token in place that goes after check application, we have a free choice between the two subsequent activities, notify client and a complete application. But what does it mean for us? That means that we get two additional traces that actually do not fit this particular process. So for instance, if the user sends the application, they already assume that this application is complete and there is no need to make the complete application step. And also similarly, the similar situation if we create application, when the bank employee creates the application, then we do not notify the client that, okay, this application doesn't contain any errors or typos. So we get additional traces that actually, for instance, for this particular process, we are not interested to see here. So how should we proceed, and how we should repair our model so that it will fit our event log? We have to construct two additional non-local dependencies between the events. We have to say that, okay, after send application, we have notify client event, and similarly after create application, we have complete application. So here how we are going to organize our repair and our enhancement algorithm. We're going to add, by means of Petri nets, we're going to add additional constraints to our model so that it will fit better, it will be more precise, and it will fit the event log. For this, we will have to apply region-based synthesis theory that is used in process mining, and this theory is well known for being very precise in generating process models. So let us consider So here at the bottom of the slide, you can see a transition system that was constructed from this event log. So here you can see the transition system at the bottom of the slide, and at the top of the slide, you can see a Petri net that we just discovered applying our split minor or inductive minor algorithms. And in Petri net, we have a place that is a free choice place where we choose between notify client and complete application, while in our transition system that corresponds to our event log, we have two corresponding states that are S4 and S5 that both correspond to the same marking of our initial Petri net, of our discovered Petri net. And of course, our transition system is precise, it is perfect. It perfectly represents the event log. But if we talk about the process model, if we talk about the Petri net, we can't distinguish between these two states S4 and S5 because they correspond to the same marking. And this is the problem that can be solved using the region-based theory that works with transition systems constructed from event logs. And let's see how we can do this. We can find these non-local constraints by applying this theory to the transition system and by constructing additional places. So the region-based theory is known as a theory that finds these places that in Petri nets that are constraints that restrict the behavior. And here we can see how we can enhance our model. We add two additional places from send application to notify client and from create application to complete application. And this model perfectly corresponds to our event log because we have added these two additional constraints that are not local and that can connect different parts of our process and helping us to be closer, to be more precise, to be closer to the event log. So now I'm going to tell a little bit more about state-based region synthesis algorithm and how does it work, because it relates to the repair algorithm I'm going to talk about later. So suppose we have a transition system. Also, so I think that you can ask me what is the difference between transition system and finite state automata. So here, okay, we can say that actually it's a matter of taste, and here we do not have, since we have the finite number of states in our transition system, we can still say that it's a finite state automata. And we have this automata model that is constructed from event logs. The synthesis-based region algorithm can work even with models that contain loops, but here we will not contain any loops because we construct our model from the event log. So these are sequential traces, and we can, for instance, minimize this model so that it will contain less number of states, but still it will not contain any loops. And we can apply the synthesis theory. So how does this theory work? It covers our transition system with regions, and each region corresponds to a set of states. So, but not every subset of states of our transition system is called a region. There is a special definition that is here, that is represented here. So what we will call a region. A region is such a subset of states that the following conditions hold. For each event, we can pick any event. So we have an event log, and there are many events there, the names of the activities. We pick each such a name, and we call our subset of states a region if and only if one of the three conditions hold. This event is either enters our region, so all the arc in the entire transition system labeled by this event enter our region, or they exit our region. So the source node is inside the region, the target node is outside the region, or they do not cross our region. So this is the third condition. So it's our arc that is labeled by our event is either inside, so both nodes are inside our region, or both are outside, so we do not cross the border of our region. So this is the main definition of the region, and the main definition that is used to synthesize places. So here, let us consider our transition system and find these regions. So here we have only minimal regions. So there is no other region that can be inside the given regions. Because, for instance, you can tell me, okay, I put all the states from S1 to S7 into one set. This is still a subset, and this is a region. There is no contradiction, okay? I totally agree, but here we consider only minimal regions. So first, for instance, let us consider region R1. So check application enters this region. So all the arcs, all the edges of our transition system labeled by check application, they enter our region. This is true. There are only two of them, and both of them enter. So that works good. Then we have two events, notify client and complete application, and they exit our region. All other events do not cross. So it works. And if we will take a look at all other regions of this transition system, we will see that they all meet this definition. I pick any event, and for each event, I know its type. For the whole transition system, I say all the arcs labeled by this event enter, or all of them exit, or all of them do not cross. This should work. And then I say, okay, this is a region. So, and then our synthesis algorithm transforms each region to a place of the pattern net. So how does it work? So it's really easy. Since we know the names of all events that enter and all events that exit and all that do not cross, we exactly know how to connect our place. We know where we have input transition system, input transitions and output transitions, just according to definition of the region. So this is how it works. And if we apply the region theory to our transition system, we get two additional places that were not considered before. These are R2 and R3 that give us this long distance dependencies that we were not able to discover by constructing directly follow graphs, because directly follow graphs is an abstraction. Okay, but how to find them? We will apply the region-based synthesis theory, but we will not do it from scratch. We will not take our entire event log and apply the synthesis theory. First of all, because the models are discovered by the region algorithm are rather convoluted. So we still want to discover our skeleton, our nice free choice and very simple model. And maybe after that, if we miss some non-local dependencies, we will be happy to restore them, to recover them by applying region-based synthesis techniques. This technique actually solves the two main problems. The first problem, and then I will formulate how we apply and how we use these two problems in our context when we need to restore these non-local dependencies. So the region synthesis theory works with solves two different problems. The first is known as state separation problem. So we say that we solve the state separation problem for two different states S and S prime if we are able to find such a region that one state belongs to this region and other does not. So this is highly related to the minimization of finite state automata. Because in finite state automata, there can be such states that are actually equal, and the synthesis algorithm usually, not usually, but is never able to solve it, because it incorporates the minimization, and when it sees these two states, it merges it into one. So but for other states that are not equal in terms of minimization of finite state automata, we expecting, but this is of course not always solvable, but we're expecting from our state-based region synthesis algorithm to solve this problem. So this is one type of problem that is highly related to the minimization in finite state automata theory. And one more problem is called event state separation problem. And this problem will be more related to what I'm going to talk about later. So event state separation problem is a problem defined for a state and an event. So suppose we have a state such that there is no exit arc labeled by this event. Then we expect our state region synthesis algorithm to find such a region that will contain S, but E will not exit. So I will return to this a little bit later. So this is the second problem we're expecting our algorithm to solve. And there is a well-known theorem, so that is related to the algorithm presented in our work, that says that a transition system can be synthesized into safe Petri net such that its reachability graph is isomorphic to this transition system, if and only if all these state separation and event state separation problems are solvable. So for instance, if we have a transition system with two equal states, if we start if we consider all the strings, all the sequences that lead us to final states from the states, these two sets are equal. So we can't distinguish between these two states. So that means that, during the synthesis, these states will be merged into one, and as P problem will not be solved, and indeed, that means that the reachability graph will not be isomorphic to the transition system, because we will have two states merged. So this is the theorem that corresponds to what we're doing here. And so what is the relation between the state-based region theory and the repair algorithm I'm talking about? So actually, in our algorithm, we are trying to solve ESSP problems. So I can explain it on this example. So for instance, in our simplified model, in our abstract model with free choice constructs, where we can freely choose between notify client and complete application, that means that we put two states, S4 and S5 together. But how can state-based region synthesis help us here? We can solve two problems. Namely, we have to recover and to repair our model, we have to solve ESSP problem for S4 complete application that will find a region such that it will contain S4, but there will be no outgoing transition labeled by complete application. In other words, that means that we have to find such a constraint, such a region that we will not be able to execute complete application if we are in state S4. And we can find this. So here we can find R2. And similarly, the similar situation is for state S5. We don't want notify client to be executed in state S5 because it contradicts our initial event log. And that means we have to to solve this problem. So since this synthesis algorithm is known that it's time consuming, we restrict it and we have our benefits. First, we get our nice clear skeleton of the model. And the second thing, we do not solve all the possible problems. We do not consider all pairs of states and events when we construct our places. We only need to solve specific problems. But how we identify these problems? So it's this is a rather straightforward algorithm. We take our free choice Petri net, we analyze all free choice places, and then we analyze event log, transition system constructed from the event log, and we in all the corresponding states that have the same outgoing events, we trying to understand, are they really free choice? As for really free choice, can we do notify client and complete application being an SS4? And the answer is no. According to the real event log, we can't do complete application there. And then they say, okay, we have a false free choice relation in S4. And similarly, we have false free choice relation in S5 because we can do complete application there, but we can't do notify client. So that is the two false free choice relations we have discovered. And then we, for these states, we formulate this event state separation problems and we solve them. So these are basic ideas of this algorithm and how it works. So what about the properties? Okay, so we applied this nice region-based synthesis. We generated these new places. We put these new places and we injected these places to our models. But what about the basic properties of the models that we discover, what we have discovered applying these techniques? So first of all, fitness. The first theorem says that the fitness is preserved. So if we have a trace that we were able to replay, that first of all, it belongs to our event log, and if we were able to replay this trace in our model, we're still able to replay this trace in our new model. But of course, this trace should be in event log. And precision should not, we can get only better precision. According to the second theorem, the language of the new model that we discovered is included inside the language of our old model. And so precision can be the same or it can be better. That's what this theorem says. So we preserve fitness, so we can still replay all the traces we were able to replay from our event log, and we can make the precision better. So these are the main two theoretical outcomes of our work. And then, of course, so we ran some experiments. We took small toy models, first of all, and we applied a plugin that was implemented within a-posteriori platform, community edition. And here you can see the number of places and the precision for different artificial models. So blue dots represent models before the repair algorithm was applied, and orange dots represent the models that were discovered that are a result of the application of the repair algorithm. And of course here, why do I have such a perfect fitness? Of course, because these models are rather simple and the event logs were generated from the models. So these are rather simple examples here. But also what we did as an extension of this work, we took real life event logs and we apply the algorithms. And here you can see a list of real-life event logs that are BPI challenge event logs. And we can see the number of new places that were generated additionally by our repair algorithm. And here we can see that precision is better. We have better precision. And what is good, so we've managed to design and to engineer this algorithm in such a way that the time for these calculations was less than a second. That's a very promising for a region-based synthesis, because we know so it really takes time to apply this synthesis, although we get this perfectly fitting and perfectly precise models. So these are application to real-life event logs, and here one of these event logs. So, and this is the model. The solid part is the model discovered by inductive miner from the real-life event log, and the dashed part corresponds to a new place that was discovered by the repair algorithm. So actually, how does it work? If we make resolve or update step, that means that we will not make caused by CI. As far as I remember, this process considers applications. So, and if there is some modification of an application, then the caused by CI event fires. But if the application was resolved or updated, and this somehow a closed process, then it should take other parts. So this is how it works. And we get models that we have more than one final marking. So maybe you will notice this, that if, for instance, no one of resolved and update transitions, no one of them fire, we still have a token in place R. So, and then we will get a final marking that is RP12. So yeah, we construct, we get nets where we do not necessarily have only one finite marking. We also considered how to apply this approach for, let's say, more high-level models represented by in high-level languages such as BPMN. And now one of the ways, so as you know, BPMN is a flow chart language where we can't really model non-free choice constructs. And of course, if we have free choice Petri nets, they're easily converted to BPMN models. But how to be with our additional places that we have discovered? For instance, one of the options for BPMN, since BPMN contains a lot of elements that are not of them are widely used, but for instance, the data perspective is rather common for BPMN models. And what we can do, we can create a variable that is called application time and assume that send application and create application to our tasks from our motivating example. They somehow change the value of this variable, and then we have when we have to choose the branch, we can decide where we can look at the type of the application and decide basing on the type of application. Was it application sent by client, or was not sent by client? Was it somehow handled the banking side? So this is how the one approach how we can represent these long dependencies. The other approach is based on signals, but according to the BPMN semantics, so the semantics of signals are not very strictly defined. So in the specification, it's said that signals are super global. So they're not even, they're not on the level of the process instance. They are on the level of the process that also covers all process instances. So for instance, if I send a signal, that means that not only this particular process instance will see the signal, but all the processes instances running now in the system. So, but in many let's say commercial BPMN tools, BPMN execution tools, signals are used locally. So it's still possible to model this with signals. So thank you very much for your attention, and I will be happy to answer your questions.
Thank you, Anna. So it was a very interesting talk, and
Thank you.
so nicely presented. Very interesting. So just questions, please. I saw that Sergey has a question. Yeah.
I had one. Sorry.
Yeah.
I had one regarding just the statement about the claim about just that so for a transition system it's possible to make a pattern net. So there is a reachability graph is isomorphic. So I guess it's only some subclass of transition system for which such a statement is. So just such a statement holds, because so in general case, namely for elementary transition systems. So did you consider exactly this subclass, and maybe it somehow correlates to the free choice pattern nets? So you simply just you didn't mention such a restriction, but there is one.
Yeah, Sergey, thank you very much. As far as I remember, this elementary transition systems corresponds to the systems where we can exactly solve these SSP and ESSP problems. So of course, not always we can construct. We can synthesize a pattern net with a isomorphic graph, and the theorem says that these two problems, if and only if these two problems are solved for all events and for all the states of the transition system, then we can synthesize a model with isomorphic reachability graph.
Okay, so am I correct that in your work, so just one of the most important requirements for such a transition system or transition systems is that you need to satisfy the state separation property, yeah? So is it
yes. So yeah, no, not of course for all. So here is this theorem. So we can synthesize a safe pattern net with isomorphic reachability graph if SSP and ESSP problems are solvable. So this relates. I'm sorry, this is a very good question. Thank you. I would be honest, I don't remember the definition of elementary, but something tells me that this definition is somehow related to this to SSP. First, as far as I remember, the elementary transition system is a minimal transition system for the given language, and this relates to state separation problem, the minimality. And the second problem, that is event state separation problem, as far as I remember, yeah, I think I remember the definition, is related to so-called excitation region problem. So this is just another formulation, another notion of elementary transition systems. So first, minimality, this corresponds to state separation problem. And the second is about excitation regions. And this is exactly event state separation problem. So a region is for each region, if we have an exit event, and an exit transition labeled by some event, let's say A, we should have all the states. I remember. So yeah.
So as I could.
Yep.
So it must be another property satisfied for elementary transition system. So the first one is about state separation, and the second one is just forward closure property. It was just
yes. It exactly corresponds to event state separation problem. So these are just if we say we have SSP and ESSP, that means that we have these elementary transition systems, and this is what this theorem tells us about. Yeah, so these are. about the same things.
So here in this theorem, you may so simply substitute this part. That's so we just may we rephrase this theorem that the transition system can be synthesized. So I'm not actually sure that I get precisely what does it mean. A transition system can be synthesized. It can be used for synthesize. Maybe just I say better than that. So is this the sense? Can be synthesized into. Well, okay. So just a transition system can be synthesized into net. So such that if this transition system is an element weight, or these two properties SSP and ESSP makes this transition system just this class of transition systems are narrower than just the class of elementary. So again, let me reformulate my question. So the question is, if we consider a class of elementary transition systems with these two axioms, I mean this relation property, which is seems SSP property in this theorem, and the forward closure property. So, and if we consider another class of transition system which satisfy to this SSP, which seems the same, and ESSP, would it be two equal classes, equivalent classes? Close. So what the problem is?
It seems that Anna has internet connection problem.
Not me, because oh, okay, great. Can you hear me? Sorry.
Yes.
Okay.
Anna has some problem.
Yeah, Anna freeze. Took.
Because it's too far, so far from Moscow, Melbourne. Far from, yeah. So this is just well. So this it seems someone is trying to reconnect right now.
I think just a minute or two.
That this topic is just intersects a bit.
Sergey, sorry, so you are speaking far from your microphone.
That's how these topics correlates to what I've done with my PhD.
Yeah. So
I'm sorry, my connection is very unstable. In two words, I can answer. Sorry.
Yes, we return to your answer. Yeah.
So SPSP and ESPSP problem is exactly about this elementary. So this is about the same thing. So you can replace in this theorem is isomorphic if TS is elementary.
So I just wanted to clarify this point. Yeah, thank you. Yeah.
So more questions, please. So Vladimir Anatolyevich,
I see. Good. May I ask a question, a quite naive question? And what if at the beginning, when building a free choice Petrinet, we'll use not the ordinary Petrinet, but a colored Petrinet by associating a certain specific color with every log, and then building transitions with the using of this coloring. Perhaps maybe some effects perhaps this trick may be effective for operating with these histories. Is it really an idea or not?
Yes, that's very interesting question. I've never been thinking about that. But I think that by event log actually you mean trace. So we have one event log and we have many traces there, and we give a color to each trace of our event log, and then yes, that's very interesting. But we will have really. So we will have thousands of colors for real life event logs, and then we will need to understand what are the traces of the same color, because we do not want to distinguish them, because we think that they do not have these long dependencies and we want to generalize. Yeah, so that's a very interesting question Thank you very much. I think it's an interesting idea. Just as if I understand you correctly, so you say, okay, don't go for this BPMN with data that is actually can be considered as Petri net with, but consider it from the very beginning. Yes, and then when we have these colors, we will know this. We will know this long distance dependencies because of the colors. But of course, in this case, we will get really massive
It seems we will
Communicate, yes.
Okay. It was
I'm very sorry.
When we was talking, yeah, the main part of the talk, yeah.
So the idea is very interesting. Thank you to consider this repair already at the discovery stage of the algorithm. But then we also will have to deal with huge, convoluted, and complicated process models because we'll have hundreds of colors, and we need, for instance, only 2-3 long distance dependencies. We don't need that much, so we will need to
certainly, yes, I see the problem, but now we'll have another problem, the problem of coloring minimization.
Yes, exactly. That's a very interesting direction. Thank you. I've never thought about this before.
Yeah, more questions?
Yeah, I have one more. So Anna, could you please show us the slide, a slide or a series of slides regarding the essential part of the minimization of your novel repairing algorithm? So just want to.
Yeah. Sorry, what slide?
Which describe the essential part of your algorithm, of newly suggested algorithm.
Actually, let me find it. So we can describe it. So here, so I show the algorithm by examples. In the paper, I have the pseudocode, but here I just have, so I decided to give some examples. So first part of the algorithm, we find this false free choice constructs. So we find these places and then we formulate this problem as, let me find it, and then we formulate it as ESSP problem, and then we apply the standard classical synthesis technique, but not for the whole transition system of just for the pair, the state and the event. So I'm sorry, I do not have the pseudocode here, but
okay.
but the algorithm works in 2 steps.
Okay, so am I correct that so the problem is reducible just to some classical approach based on the series of regions,
Yeah.
but applied for some local pieces of your model which are detected by some sophisticated approach as to be needed to reconstruct it. Yeah.
I'm sorry. I think I have problems with my connection. Could you please repeat the question?
I just want to clarify.
With microphone, Sergey. So could you hold it somewhere other way?
Maybe.
When you're looking so aside, so we can't hear you, understand you at least.
Oh, so can you hear me better?
Yes.
Much better.
Sorry, it was wrong. So it was wrong source of for my microphone. I'm so sorry. So I just wanted, I just wanted to clarify whether just the problem described in the paper, in your talk, is reducible just to the some classical approach. I mean, some classical they mentioned so just algorithm based on the theory of regions, but applied only for some local pieces of a model, which so were detected previously by your novel sophisticated approach that to be needed to reconstruct it.
Yes, exactly. Yeah, thank you for the question. Exactly. It's a classical approach applied to only some parts of the transition system. And the first step is not really sophisticated. I mean, the detection of this false free choice relation is not hard to do. It just in one go through the transition system. First, I look at the Petrinet and I find all the choice places, and I assume that the Petrinet is a free choice Petrinet. I find all the choice places there. Then for all these choice places, I find the outgoing transitions. Then I find these outgoing transitions in my transition system. And then I check that all the source nodes, all the source states there do have outgoing transitions labeled, all of them. So I expect S4 to have outgoing transitions labeled by notify client and complete application. So both of them. Here I do not see both of them in S4, and that is why I claim that S4 is a false free choice relation. So it's not sophisticated. It's not. So it's very straightforward. So I say, okay, then S4 is a false free choice, and S5 as well, symmetrically. And then I say, okay, but what should I solve? And then I exactly right from this point, I formulate two SSP problems. I have to restrict S4 not to be able to execute complete application, and I formulate it as SSP problem. And I want S5 not to be able to fire notify client, and I formulate one more problem, but of course not all of them. But the first part of my algorithm is really straightforward. Now maybe it took some time to give the definition of a false free choice relation, to prove fitness and precision, and of course to implement and run all the experiments. Yes, but this is a standard synthesis algorithm.
Well, okay, so I have two more questions, but am I allowed just to ask at least one?
Yeah.
Okay. So the first question is, did you estimate any complexity of the algorithm you have developed in terms of
yes. Unfortunately, it's the same because if we deal with NP, we just divide our NP. So we have this complex problem, NP problem, as SP is known. And the point here is that we do not have to solve all of them, and only, for instance, here only two, but they still NP problems.
So it's exponential. Yeah, in terms
yes, it's still, unfortunately, the only things to do, we prune our tree of solutions. Somehow we cut unnecessary branches, and we, for instance, if I have a goal, I want to find a region such that it contains S4 and it doesn't have complete application as exit. I already have two constraints for this. I do not consider all possible regions. I already put myself into this constraint. So when I construct this huge tree of possible solutions, of possible regions, I cut off some of the branches. But still, from the theoretical point of view, it's NP. From the practical point of view, it's better. So it could be better. It could be better because we cut something. But still, I can give you an example where it will explode.
Okay, so but the question is, so do you have any benefits on that? So you apply the region algorithm not for the model entirely, for the entire model, but just to some small pieces of this model. So
yes,
as so just in the paper of Van Ralst about the maximal decomposition, you see when so just an exponential approach is applied.
Yeah.
Minimal elements, and so we have some benefits because
yes.
of, you know that just at the beginning part of these exponential functions, so it's quite fast.
Yes. So yeah, here I was happy and surprised to know that the time is still really good. So it's less than a second. So here in this table, you can see for real life event logs, I didn't simplify these event logs. I did not filter them. So these are just event logs that I have downloaded from BPI challenge site. And the time is very acceptable, I would say. So it's less than a second, while if, for instance, we take the whole transition system and we try to apply the synthesis algorithm to the whole transition system.
But which one? So the initial, so as far as I understand, so
they're the same.
Repairing, but so the initial system was synthesized by using which algorithm?
Just we just put all the traces together into one automata model and then minimize it. Let's say that. So we have a huge automata model that doesn't contain loops, and then can replay all the traces from the event log and only them. So this is the approach to represent the event log as a transition system.
And then to apply the region-based algorithm for
yes.
for the whole transition system, yeah?
For the whole, it's rather complicated, and I tried this in Prom, and it seems that, I don't know, is it the problem of implementation, but also, of course, it's a problem of algorithm. It never stops, so it's still calculating and calculating. But here we really have strong restrictions. And of course, it's not like a miracle, you know, you had an NP problem and now we can solve it within 1 second. Not of course, because we still construct models that are not perfect. And if we'll look at them here, not artificial that I showed in the previous slide, but here you see that the precision of the new model is just better, but it's not one. It is still, we still didn't solve the synthesis problem. We just a little bit improved. Everywhere where possible, we inject at these places, but we still deal. These are only subsets of all huge space of the possible regions. Yes, so yeah, the answer is that we didn't solve the whole synthesis problem in 1 second. We just a little bit improved our skeleton free choice model everywhere where we could.
Yeah, thank you.
Thank you. So Anna, so just a very short question. So could you switch to the next slide 20 with your example? So my question was, so just the initial model was sound, I guess, yes? But when you add this new, I couldn't see it, but it looks like it is not sound now.
Yes, exactly. So if we take the classical definition of soundness, where we have one initial marking and one final marking, we already do not have soundness here because we have two final markings. We have one final marking that is P12 and another that is P12 plus R, because we can leave the token in R. Yes, exactly. That we do not guarantee soundness in this sense, but this is a very good question. Thank you, because yes, we are good in fitness and precision, but it will be good also to consider also, yes, we can still have these missed tokens at the end of the process execution. That is true. What we will not break the boundness because we only add places. Yes, but we can end up with this model. Yes, and this is an example that is described also in the paper, that yes, we have more final markings now, good or bad, but this is how it works. And in the classical according to the classical definition, this model is not sound.
Yeah, thank you. And is it true that actually with this region technique, you can find, I would say, these causality dependencies. Yes, so just for not very far to say events, you see, because you catch them with regions, yes, but they may be somehow in very different parts of the model. Is it true?
Yeah, so not really. I think that regions can be really large, so there are no restrictions, and if there is a very long distance, the region theories can still find it, because it will explore all the states until it finds the region. And if the distance is really long, it doesn't matter. It will continue until it finds it. So no, for the region theory, it's not a problem. The size of the region can vary.
Yes, but there are causality relations which can't be found with regions, of course.
Sorry?
There are some causality relations which can't be found with regions with this approach. Should be, I guess, I'm not sure.
Actually, this region synthesis approach is very strong in terms of precision and fitness. So yeah. So if we have these conditions hold, if we hold these conditions, SP, SSP, SSP, this one, then we generate the Petri net that perfectly matches isomorphic. That is isomorphic. So, and if the long dependence was in the event log, it will eventually be in the synthesized Petri net. So in this, so the synthesis approach is very strict, and yeah, that's what I was trying to explore in this work.
Thank you.
Thank you.
More questions? So Anna, thank you once more for the very interesting talk. And actually, there are some interesting questions to think about, really. So just how to use this additional information to make models better. And so, as I told, this was the closing for this series, I would say, of our seminars. And we hope to meet in autumn, winter.
Thank you very much for inviting me. It was my pleasure to give a talk at your seminar.
Thank you to all participants.
Thank you for very
Thank you.
talk.
Thanks.
Bye. Bye.
Bye.
Thank you. Goodbye.
Goodbye.